Okay, so what I was trying to say was that the curvature of a curve is defined in this manner. If you have a curve which depends on the parameter t, and if the parameter is unit speed, then the curvature is simply the magnitude of the second order derivative of that alpha with respect to the arc length s, or unit speed parameter. And this, of course, is for a regular curve, because as you know, alpha dot t is in the denominator, so it won't be defined if the derivative vanishes. So now we want to somehow so I want to define this curvature somehow on a surface, on a point at a surface. I want to define the curvature of the surface at a point instead of a curve at a point. That's what we are going in this unit third. That's the goal. Now for that, we start with what we call this. We look at the surface. Now this is how I draw a surface, not a part of it. Imagine this is inside R3. I got X, Y, and Z. This is how I draw it. So now I assume that this surface is regular, so that I can draw a tangent plane at this point to the curve. So tangent is just touching at this point, and of course ये जो tangent plane to the surface होगा, इसका जो normal होगा, यानी perpendicular vector to this plane. So उसको हम denote करते हैं by this capital N, and it is equal to R sub U. में क्या होगा, R sub B divided by the magnitude of this RU cross R. Okay, so of course our surface is given by this vector R depends upon R at U. So that's our regular surface. Now what we do, we want to somehow come to a definition of curvature, the degree of curvedness of the surface at a point. So that's what we're going to do. But for that, we're going to use the idea of the curvature of a curve. By that I mean, let's first define for that what we call a normal section. So normal section of a surface को हम define करेंगे. Now what I mean by that, now let me just take an example. So if my curve is if my surface is suppose a sphere, so sphere, I usually draw it like this. Dot का मतलब ये है कि इसका एक 3-dimensional picture है. It's a sphere, not a circle. ये dotted line जो मैं डालता हूँ. Now if I intersect a plane, of course it's infinite, it extends infinitely. But if I intersect it with the sphere, there would be a curve intersection. तो इसके जो intersection का जो curve होगा, as you can see what it would be a circle. When I intersect this sphere by a plane, this surface by a plane, so I will get a curve of intersection, the curve which lies on the plane as well as the sphere itself. So in this case, it would be a circle. I will call it a section of this sphere by this plane. जो यहाँ plane pi है, मान लो ये sphere मेरा S2. So similarly, suppose I had a cylinder. Cylinder नहीं लेते, cylinder लेते. Now suppose I intersect it by a plane parallel to the generator. If I intersect this, so imagine you are cutting through this cylinder by a plane. So curve of intersection would be a pair of parallel lines. And if you intersect it by a plane perpendicular to the generator of this cylinder, so what the curve of intersection would be a circle. And there would be many others. Similarly, you know about conic sections. If you take a cone and intersect it with a plane, of course, So if you intersect it with a plane that is parallel to the generator, so you will get a curve that's called a parabola. And probably it would be a parabola. And of course, if it is not a parallel, then there would be two possibilities. If it cuts the one part, if it cuts it in this manner, not parallel to the generator, so जो curve होगी intersection की, जो section जो होगा वो by ellipse. इसी तरह से another possibility would be that of a hyperbola, and of course there would be degenerate cases of a pair of lines on a line or a point. Okay, now these are all sections of surfaces by planes. Now similarly, there is something called a normal section of a surface. If I have a surface, right, and I cut that surface via a plane which contains this normal, and which must contain this vector n, the surface normal. तो ये जो curve of intersection बनेगी, in this case अगर मैं इसको roughly draw करूं, तो अगर ये surface पे है मेरा, तो ये है मेरा the section of this surface by this plane which contains the surface normal. इस curve को हम कहते हैं normal section. So you just have to imagine it a bit, और अगर book से भी देखोगे तो ज़्यादा better होगा. So वही मैं लिखूंगा. Let me write down a simple definition first. A plane drawn through a point on a surface cuts it in a curve. जो जहां पर है अपनी curve, cuts it in a curve called the section of the surface. Called the section of the surface rather. If the plane contains the normal to the surface at that point, if the plane contains the normal to the surface at that point, then the curve is called the normal section. The normal section. Otherwise, it's called an oblique section. The principal normal, जैसे कि तुम्हें पता है, तो पहले तो मैं ये जरा ये अपना हो गया definition. So this would be the normal section of the surface at this point. So अगर तुम स्फीयर की एग्जांपल लो, now इसका भी एक surface normal है, यानी a tangent plane जो हर एक जगह हम डाल सकते हैं. तो अगर कोई plane है which contains the surface normal, चलो मैं दूसरा बना सकता हूँ यहाँ पे. Okay, जैसे स्फीयर में है normal sections हम चेक कर सकते हैं. So I take the surface of a sphere and of course it has a surface normal. यहाँ पे मान लो मैं एक tangent plane डालता हूँ, तो of course यहाँ इस तरफ इसकी एक surface normal निकल रही है. तो अगर कोई plane है which cuts this, which contains this n, it would intersect this sphere in a circle, and that circle would be the great circle, the circle which has the same radius as that of the sphere. But if it does not contain, suppose कोई ऐसा plane है which does not contain the surface normal at that point, so it again would be a circle, but it won't be the great circle. So oblique section जो यहाँ पे होगा, it would be a circle, but not the great circle. But normal section जो होगा, it would always be the great circle. So of course now पहली बात तो ये कि normal section is a curve on a surface. तो अभी तक जो हम कह सकते हैं, तो normal section at a point on a surface is a curve on a surface. Is a curve on a surface, अगर मैं इसको इस तरह से लिखूं, that is the intersection, and it is the common curve of the surface and the plane that contains n at that point. Or of course, n हमेशा exist करेगा because it's a non-zero vector, because we are assuming that surface is normal. A surface is regular at each of these points. So, okay. Now, furthermore, अब जो हर एक curve जो है अपनी जो तुमने किया होगा Serif-Reney formula से, so this is the curve which has got a parameterization, so therefore it would have some direction. So there is always a triplet of vectors t, right? And then there is n. Let me write n here. वैसे लिखना नहीं चाहिए इस तरह से. Usually हम लिखते हैं जब n. But then there is a triplet of mutually perpendicular unit vectors called the Serif-Reney frame, and t is called the unit tangent vector. N is called the normal vector or the principal normal vector at that point, principal normal, and P is called the binormal vector. अब जो ये हमारी normal section है वो भी curve है, तो उससे भी related TNB होगा, but now इसका जो principal normal होगा vector N, it would be parallel to the surface normal N at that point. So that's rather obvious मुझे लगता है, क्योंकि अगर तुम्हारे पास कोई curve है और इसका एक principal section है, it would lie inside a plane which contains N. Of course, अगर ये tangent होगा इस point पे यहाँ पे, तो कहीं इधर इसका depending upon the orientation of the curve का जो आपने parameterize कैसे किया है. So T या तो इस direction में होगा या फिर इसी direction में होगा. In any case, it would be parallel to the big N, the surface normal at that point. तो curve का जो principal normal है, that would be तो वही मैं यहाँ लिखूंगा, the principal normal to the normal section जो कि curve है, which is a curve, is parallel to the normal to the surface. It's parallel to the normal to the surface N. अब depending upon the मैं बताऊँ T का अब कैसे parameterize करते हो अपनी उस normal section को, it could be either in the same direction or in the opposite direction. Now we want to find the curvature of this curve. This is a curve here on a surface which lies in the plane that contains the surface normal. So we want to evaluate its curvature in terms of the first and second order fundamental magnitudes. जो कि तुमने किया होगा, first order fundamental magnitudes होते हैं E of G, the second order fundamental magnitudes होते हैं L and M. दोनों की तुम्हें पढ़ी होगी significance, इनका जो what do they mean, how are they related to the surface. Okay, now वही हम करेंगे, हम इसका curvature ढूंढने की कोशिश करेंगे. Curvature of normal section in terms of the fundamental magnitudes. Fundamental magnitudes. So let's start with let Kn, K sub n, denote the curvature of the normal section. Denote the curvature of the normal section. then kn of course is positive always. Curvature जो है by definition is modulus of something, therefore it is positive. When it depend करता है क्योंकि ये प्लेन कर्व है तो ये पॉजिटिव नेगेटिव भी हो सकता है. जैसे ये कर्वेचर है ना, इट लाइज इनसाइड अ प्लेन. अब प्लेन कर्व में तुमने क्या होगा, वी कैन असाइन अ साइन टू द कर्वेचर, जिसको हम कहते हैं साइन कर्वेचर. तो यहाँ पर भी हम मतलब कर्वेचर मतलब एक असाइन करेंगे इसको साइन, बिकॉज प्रॉब्लम है कि अगर हमारी सरफेस को हम ऐसे है कोई सरफेस, तो यहाँ पर जो कर्वेचर ऑफ द नॉर्मल सेक्शन कर्व कुछ इस तरह से होगी जो ना इंटरसेक्शन ऑफ द प्लेन एंड दिस सरफेस होगी. और अगर इन केस यू हैव गॉट a surface in this, ये गाना कौन सुन रहा है, वो भी कश्मीरी. तो there would be a curve in this direction. तो हम एक convention fix करना चाहते हैं to distinguish these two cases. You know, इसका curvature obviously should be मतलब of opposite sign to that of this. तो एक convention fix हम करेंगे कि हम इसको मानेंगे positive when the curve जो है is concave on the side which n points out. क्योंकि n में भी हम obviously convention तो fix करते ही हैं. n जब मैं कहता हूँ is ru cross rv divided by this magnitude of this vector, so obviously there is a choice of sign. तो उसको अब इसके साथ क्योंकि मतलब surface मतलब जब भी मैं कोई दो वेक्टर्स लेता हूँ ए बी इन दिस प्लेन से, तो अब ए क्रॉस बी की दो पॉसिबल साइन हो सकती है, या तो ये वाला तो या फिर मतलब कमिंग आउट ऑफ द स्क्रीन और गोइंग इनसाइड द स्क्रीन. फिर हम कन्वेंशनली ये मान लेते हैं कि ये इस तरह से होगा कि ए बी सी मतलब या ए बी ए क्रॉस बी शुड फॉर्म अ राइट हैंडेड सिस्टम. तो राइट हैंडेड सिस्टम के हिसाब से अगर ये ए है और ये बी है, तो ये जो ऊपर जा रहा है वो हमारा ए क्रॉस बी है. Well, that is just a convention to choose a direction of A cross B once we know the direction of A and B. So same applies to this surface normal N. Now what we do, so अगर N बाहर की तरफ आ रहा है और कर्व उस साइड पे इस तरह से है, कॉन्केव है, तो फिर हम कहते हैं ये जो इस कर्व का जो कर्वेचर है इस नॉर्मल सेक्शन का, उसको हम पॉजिटिव मानेंगे. Okay, when the curve is concave on the side on which the n points out. और अगर उसका उल्टा है, तो अगर n इस डायरेक्शन में जा रहा है, राइट, और कर्व इस तरह से है नीचे की तरफ, अगर n की डायरेक्शन हमने ये ली है, तो हम मानेंगे ये जो ये प्रिंसिपल सेक्शन है या इसका कर्वेचर नेगेटिव है. Although in the final analysis it doesn't make much of a difference because curvature ultimately has to do with the magnitude of something. But it is important here because we have already made a choice for n, so we have to make a choice for kn. Okay, now we know that if t is the unit tangent vector of the normal section, of this curve on the surface, normal section, then dt differentiated with respect to the arc length is equal to r double dash, that is t dash, and we know that this is k sub n, right, because kn is the curvature of the normal section. This is one of the Serifan equations, but this is equal to kn n. Now with my choice of sign of मतलब basically हम चाहते थे ये जो मैंने कहा ना कि अगर इस तरह से है तो इनकी ऑपोजिट डायरेक्शन होगी, इस तरह से अगर n बाहर की तरफ जा रहा है तो और एक ऐसी है तो n kn को हम नेगेटिव मानेंगे. That would imply we are aligning n and n. That's the only thing. The principal normal and the normal of the surface को हम एक ही डायरेक्शन में मान रहे हैं. so that this is true. And I can replace the small n by the capital N. Therefore, Kn is मतलब अगर मैं दोनों sides बोलूं dot product with n, so this would be r double dash dot product with n. अब क्योंकि n dot n 1 होगा because it's a vector of magnitude 1, so Kn should be equal to r double dash dot n. So let's call this equation 1. अब फिर हम निकालेंगे अपना what is r dash. Now r is equal to r sub u, right? Now we have to remember ये जो r है, let me थोड़ा सा यहाँ पे दिखना होगा हमें, वो ये कि मेरे पास एक सरफेस है, अब सरफेस पे एक कर्व है, वो है नॉर्मल सेक्शन, ठीक है ना? So since it lies on a surface, it is like r is equal to r uv, but it is also a curve. It's also a curve, so it would be of the equation of this type: r is equal to r at s, where s is the arc length of this curve. So अगर ये दोनों सेम है, क्योंकि ये surface पे ये इस equation को भी satisfy करता है, इस equation को भी satisfy करता है, then it should be the composition, and u and v should both depend upon s, and you should have r is equal to r at u at s, where both u and v depend upon this on this parameter, because it's a curve. It's also a set of points that lie on the surface, so it must satisfy the equation of the curve, which would be r is equal to r at s and r is equal to r at uv, which means that u and v must be some function of s as we go along this curve. Okay, once I'm done, then I have to find r dash. Now r dash is dr by ds. Now using the chain rule, this should be, जैसा कि तुमने बहुत बार अब तक यूज किया होगा, del r by del u into du by ds. It is the chain rule of the multivariate calculus. अब तक तो ये बहुत बार यूज हो चुका होगा, I mean. So this is what I should have. यानी r dash is equal to r sub u into du by ds plus r sub v into dv by ds. So this is what I should have as r dash. Now differentiating with respect to s, again, I should have r double dash, yeah, एक बार और differentiate किया, should be equal to d by ds of r sub u du by ds plus r sub v into dv by ds. Now, of course, applying the chain rule again. So what should it be? So the chain rule के हिसाब से this whole thing, पहले तो हम इसको अलग-अलग कर सकते हैं, यानी we can write it as d by ds of r sub u du ds plus r sub v, sorry, d by ds of r sub v dv by ds. Now this is a function of two variables, right? This is a function of single variable, so it should be, एक तो आना चाहिए r sub u को ऐसे ही रखेंगे, फिर होना चाहिए d by ds of du by ds plus अब du by ds को ऐसे ही रखेंगे using the chain rule, d by ds of r sub u. मैं थोड़ा ये पूरा डिटेल में कर रहा हूँ क्योंकि मैं चाहता हूँ कि ये बिल्कुल क्लियर हो जाए, प्लस इसी तरह से r sub v को ऐसे ही रखेंगे, then you would have d by ds of dv by ds. Then I would have also dv by ds को ऐसे ही रखेंगे into d by ds of r sub v. अब ये तो खैर सेटल्ड है, सिंगल वेरिएबल की फंक्शन है, लेकिन यहाँ पे हमें ये जो d by ds ru जो है, ru is a function of both u and v, so I have to apply chain rule. So it should be, यहाँ तो सिंपली मिलना चाहिए ru into second derivative of u with respect to s. इसी तरह से इस टर्म को भी मैं वैसे ही लूंगा, नहीं यहाँ पे plus r sub v into second derivative of s with respect to v square है square of v. अब यहाँ पे चेन रूल लगेगा, राइट? सो चेन रूल का मतलब du by ds ऐसे ही रहेगा. इसको डिफरेंशिएट करेंगे, मतलब चेन रूल वही है जो यहाँ पर है. अब सिंपली हमें ये लेना है, r की जगह ru है, so it should be r sub uu du by ds plus r sub uv into dv by ds. आई होप ये तुमने इस तरह किया हुआ कई बार. इसी तरह से ये दूसरा वाला जो है वो होगा dv by ds. Now that you have got r sub vu du by ds plus r sub vv dv by ds. ये सिंपली चेन रूल है जो मैंने 2 बार यूज किया. तो चेन रूल होता है ये फॉर अ फंक्शन, है ना, मैंने यहाँ लिखा फॉर अ फंक्शन ऑफ मोर देन वन वेरिएबल्स. नाउ वी जस्ट हैव टू डू सम मॉप अप. सो पहला तुम्हें मिला, इट वुड बी सिंपली r डबल डैश जो है इट शुड बी r sub u into of d square u by ds square. Then I should have plus r sub v into d2v by ds2. Then I should have du by ds multiplied by r sub uv, r sub uu into du by ds plus r sub uv into dv by ds plus इसी तरह से dv by ds into r sub uv into u by ds. I think so, yes. R sub वैसे vu होना चाहिए, but mixed partial derivatives are equal because second order partial derivatives are continuous. तो should be r sub vv into dv by ds. और ये सब करते करते इसको मैं लिख सकता हूँ r sub u, इसको मैं u डबल डैश लिखता हूँ, differentiating u with respect to v twice, with respect to s twice. इसी तरह से r sub v into v double dash. Then I should have, अगर मैं इसको लिखूँ r uu du by ds into du by ds. So I think इसको मैं लिखूंगा u dash square लिखूं सीधे, वो भी चलेगा, u dash square plus, अब इन दोनों को मैं कंबाइन कर सकता हूँ. So it would be r sub uv into twice I think u dash v dash. Then there should be a last body term that is r sub vv into v dash square, v dash cos square. Okay, so this is the expression. Now I know that अभी तक जो मैंने नीचे लिखा था, now अगर मैं equation first लूँ अपनी, let's call that equation first. ये हो गया, इसमें r double dash को मैं substitute करूँगा. So you should have kn is equal to, so therefore kn is equal to ये सारा कुछ r sub u double dash plus r sub v double dash plus r sub u dash square plus twice r sub uv u dash v dash plus r sub v dash square, whole dot product with the unit moment. Now using the fact that यहाँ लिखूंगा, using the fact that what कि ru dot n is 0, rv dot n is 0. ये तुमने इससे पहले किया होगा जब तुमने, now it's obvious because n is perpendicular to both r sub u and r sub v, because it's the cross product of the two vectors. So ये दोनों vectors 0 होने चाहिए, यानी this dot product with this should be 0. इसका dot product, अब बचे ये थी, तो उसमें भी ये भी तुमने किया होगा, and ये कि n dotted with r sub uu is equal to l. इसी तरह से n dot r sub uv is equal to m, the second order fundamental magnitudes, and n dot r sub vv is equal to this capital N. the second order fundamental magnitudes इनको हम एलिमेंट से रिप्रेजेंट करते हैं. So that कि n जो अब मिलेगा इसके साथ इसका डॉट प्रोडक्ट 0 इसके साथ तो बचा क्या ru डॉट डॉट n. So it should be इसकी जगह आना चाहिए l. So it should be l du by ds का square plus twice m times du by ds into dv by ds plus of course n into r dv by ds का square. So this should be our expression for the curvature of the normal section at a point. तो जिसको मैं लिख सकता हूँ L du square plus twice m du dv plus n dv square plus d divided by ds square, or to make it better, I write it as L du square plus twice m du dv plus n dv square divided by, what I do is ds square को मैं लिख सकता हूँ as the first differential first, what is that, fundamental form, that is e du square plus twice f du dv du dv plus g dv square. So now I get an expression in terms of the first fundamental form divided by second fundamental form. So that is the curvature of this curve called a normal section at a point on a surface. It is the first fundamental form, second fundamental form, L du square plus twice m du dv plus n dv square divided by the first fundamental form, that is the metric e du square plus twice f du dv plus g dv square. So this is the curvature of the normal section at a point. And so of course normal section जो है, so I've got at this point I've got this surface normal in this direction possibly. So I take this plane that intersects this surface and contains this surface normal, so it would be a curve of this type. So इसका जो curvature है, that would be given in terms of first and second fundamental magnitudes. And of course if you at this point you will get infinitely many normal sections. Why? I could have also rotated this curve about n. It would still, अगर मैं इसको rotate करूंगा है ना, तो curve ऐसी बनेगी इस point पे. So this would be another normal section at this point because it would still contain the surface normal n if I rotate it about n. So of course, so at this point there would be many normal sections, of course, in different directions, and of course they would correspond to the different values of this change in the parameter du dv. तो यहाँ पे एक value of du dv के लिए एक normal section का curvature मिलेगा. इसी तरह से दूसरी direction में जब हम parameter को change करेंगे, no, there would be some change of parameter involved when I go on the surface in this direction or in this direction or in that direction, and accordingly I will get different normal sections and their curvatures here. Okay, तो तुम में से सभी सुन रहे हो? सो गए सब? Anybody awake?
Yes, sir.
Good. जरा कैमरा ऑन करो. सभी कैमरा ऑन करो. Okay. तुम्हें कहीं पे समझ नहीं आ रहा है तो मुझे बता देना, ठीक है ना? मुझे उस टाइम रोकना. सर ये क्या था, ये क्या आपने किया, यहाँ कैसे हो गया, ठीक है ना? तो अभी तक हमने देखा ये जो curvature है, it obviously would be a number for a particular change in parameter du and dv जो हमने यहाँ किया था. ये जो formula है ना, it would obviously be curvature means some number. So this curvature would be some number, and of course for a certain du dv and for a certain point on the surface. तो हर एक point पे हम e f g evaluate कर सकते हैं. Lmn, these would be numbers because these are dot products of the partial derivatives at a point. तो यहाँ पे है RUV is a point जहाँ पर मैं ये principal sections ले रहा हूँ. And as you can see, so हर इसी तरह से यहाँ पर अगर मैं ये लूँ तो यहाँ पे surface normal इस direction में है, तो I would have a plane that would contain this surface normal. So accordingly, I would have many normal sections here. तो so उनका curvature होगा. अब यहाँ पे जब हम आगे करेंगे, हम देखेंगे ये जो नॉर्मल सेक्शंस बहुत सारे हैं, इनमें सबसे ज्यादा कर्वेचर किस नॉर्मल सेक्शन का है और सबसे कम कर्वेचर किस नॉर्मल सेक्शन का है. और हम दिखाएंगे ऐसे दो सेक्शंस एग्जिस्ट करते हैं कि जिसका कर्वेचर सबसे ज्यादा है और जिसका कर्वेचर सबसे कम है, और उनको हम कहेंगे प्रिंसिपल सेक्शंस. सो एनीवेज, so let's first define normal curvature. That is basically the curvature of the normal section at a point. तो I don't, चलो देख लेते हैं क्योंकि तुम्हारे वो उसमें होगा. Now let point P with position vector R sub RQV be on the surface R is equal to RQV, then the curvature, the normal curvature, yeah, then the normal curvature, let me see, normal curvature at P in the direction d sub u dv, this pair is equal to the curvature. It is the same as the curvature of the normal section, curvature at P of the normal section at P. P parallel, yeah, in the direction parallel to the direction du dv. ठीक है. so हम कहेंगे इस पोजीशन पे, इस मतलब इस पॉइंट पे इस सरफेस का नॉर्मल सेक्शन क्या है, हम कहेंगे, हम देखेंगे इसी डायरेक्शन में सरफेस पे जो कॉरेस्पॉन्डिंग चेंज आ रही है, तो उस कर्व का जो वहां पे नॉर्मल सेक्शन बनेगा बाय टेकिंग दिस प्लेन दैट इंटरसेक्ट्स द सरफेस दैट कंटेन्स द सरफेस नॉर्मल, तो उसका जो कर्वेचर होगा उसी को हम कहेंगे नॉर्मल कर्वेचर ऑफ द पॉइंट एट दिस of the surface at this point. Okay, so that's just a definition. So now let's talk about the relationship between the curvature of the normal section at a point and curvature of some oblique section. मान लो अगर दूसरा कर्व है, दूसरा प्लेन है वहां पे, एक तो मान लो अगर ये सरफेस का कोई टुकड़ा है, मैं ऐसे प्लॉट कर रहा हूँ, so I've got a normal section, right? तो उससे उसका कोई so there would be a curve which would be the intersection of this which contains the surface normal. अगर मैं कोई दूसरा plane हूँ which is not, क्या बोलते हैं, which does not contain the surface normal, but it intersects the curve at this point P. तो of course एक और curve निकलेगी, तो उसका अपना curvature होगा. दोनों का आपस में जो connection है that is given by a theorem called Meunier's theorem. So let me write down the spelling. It's Meus. It's a French mathematician. Yes, Meunier's theorem. So the theorem says that if Kn and K are curvatures of normal section, are curvatures of normal and oblique sections at a point, and at the same point, I mean, oblique sections through the same tangent line, through the same tangent line, the same tangent line, and theta, oh मैं क्या लिख रहा हूँ, and theta is the angle between the two planes, maybe between the normals of the two planes, but that would be the same, I think. Theta is the angle between these sections, between these curves, or between these planes which contain these curves, between these sections. Then the k sub n is equal to k cos of theta. Of course, it's very simple to prove. Proof भी बड़ा easy है इसका. कैसे? Let p, यानी वो तो पहले से ही है. यूँ लिख लो, since k is the curvature of the oblique section at this point, since the section is oblique, it does not contain the surface normal, you know? But its principal normal is not parallel, यानी its principal normal जो है curve का is not parallel to capital N, क्योंकि वो तो तभी होता है when it is a normal section. It's not parallel to capital N, but it will be parallel to R double dash by K, because you know that R double dash is equal to Kn. It is our Serif-Rennet formula. So N is the same as R double dash by K, so it would be parallel to this vector essentially. I mean this N, and these two must be in the same direction, obviously. If theta is the angle of intersection, or rather than angle of inclination, angle of intersection, angle of inclination of the two planes, inclination of the two sections, angle of inclination of the oblique section, angle of oblique section with the normal section, normal section touching the curve at the point under consideration, touching the curve at the point under consideration, then theta is also the angle between the normals. And if you have two plane, उनका जो angle of intersection होगा, ये एक और plane है, उनके दोनों angle theta है. So if you take the normals to to those planes, यहाँ पे दिखाना जरा मुश्किल है, तो उनके दरमियान भी angle same होगा. Theta is also, ये वैसे तुम करते हो lower classes में भी, angle between the normals to the two sections, angle between the normals to the two sections. That is the angle between R double dash by K, that is our oblique section, and जिसके साथ वो N parallel है, the principal norm, और N जिसके साथ वो जो principal section की normal alignment में है, यानी उसके parallel है. Thus, I should have, if theta is the angle between these two vectors, cos of theta, चूंकि unit vector है दोनों के दोनों, should be N dot R double dash by K, where K is the curvature of the oblique section, which would be N dot R double dash, already हमें पता है किसके बराबर है. So this is just Kn by K, which implies that Kn is equal to K cos theta. इन्हें कुछ खास इसमें करना नहीं था, it was a straightforward calculation. क्योंकि हमें पता है N dot R double dash जो है, that is the curvature of the normal section at a point, which is also equal to, जब हमने इसको evaluate किया था R double dash को in terms of the fundamental magnitude, it is equal to LD square plus twice NDU dV plus NDV square divided by EDU square plus twice FDU dV plus GdV square. Anyways, so that was our. So we can do an exercise. चलो मैं तुम्हें देता हूँ as one assignment. Calculation है, कुछ खास है नहीं. Find the curvature of the normal section. Find the curvature of the normal section of the, इसको हम helicoid कहते हैं, right helicoid, जिसकी equation होती है R is equal to U cos V, U sin V, CV. And of course, यहाँ पे जो UV are the variables and C is the constant. Just have to evaluate this thing. ये किसके बराबर होगा? तुम्हें L evaluate करना होगा, M उसके लिए different partial derivatives तुम्हें करने होंगे, जो कि ज़्यादा मसला नहीं. Now we come to जो हमें main चीज चाहिए, the principal sections and normal sections. Should we do it or should we do it tomorrow? Time क्या? We may continue. Principal sections and principal curvatures. तो वो मैं अभी बता ही चुका हूँ तुम्हें कि हम क्या करना चाहते हैं. So the normal sections of the surface at a point. एक point पे infinitely many normal sections होंगे. When you rotate that plane containing the surface normal, you will get different principal sections and normal sections at a point on the surface. The normal sections of the surface at a point which have the greatest and least curvature, which have the greatest and the least curvature are called principal sections, are called the principal sections. And the minimum and the maximal and minimal values, and the maximal and minimal values minimum values of the curvatures of their curvatures of their curvatures are called principal curvatures. Curvatures and are denoted generally by K sub A and K sub B, यानी हमारा जो Kn है उसमें जब हम ऑल पॉसिबल डायरेक्शंस में देखते हैं इसके वैल्यूज, उनमें जो सबसे बड़ा वाला है उसको हम K sub A कहते हैं और दूसरा वाला है उसको KB कहते हैं, because we look at all possible directions at that point, यानी all possible du by dv's at that point. Okay, and their corresponding radii are called principal radii of curvature. Principal radii of curvature. और तुम्हें पता है जो किसी का कर्वेचर है तो हमारे पास रो है, रेडियस ऑफ कर्वेचर इज जस्ट द रेसिप्रोकल ऑफ द कर्वेचर। तो इस वजह से है जो तुमने किया होगा कि अगर छोटा सर्कल है तो कर्वेचर ज्यादा है, बड़ा सर्कल है तो कर्वेचर कम है, मतलब we can think in terms of that because in any case जो कर्व का जो कर्वेचर होता है it is basically the curvature of the best fitting circle at that point. Anyways, जो तुमने मुझे लगता है यूनिट 1 यूनिट 2 में किया हुआ आराम से। तो if we take अब जो भी सरफेस होगी तो अब जो प्रिंसिपल कर्वेचर्स हैं किसी भी सरफेस के, ठीक है ना, तो अगर उनकी रेडिया है there will also be a center of curvature at each point of a surface of a principal section. जो कर्व्स हैं तो हर पॉइंट पे एक अपना एक center of curvature होगा, that would be the center of the best fitting circle at that point to the curve. और उनका जो लोकस बनेगा अगर हम उनका पाथ ट्रेस करें we call that surface of centers, तो वो भी एक surface generate करती है, parallel surface, मतलब the corresponding surface, ना parallel in that sense, जिसको हम कहते हैं the surface of centers, जो मैं लिख देता हूँ it is just an information. Locus of the centers principal curvatures at all points of a given surface is called its surface of centers. The directions of the principal sections, यानी जो दो खास normal sections हैं उनको हम कहते हैं principal directions. The directions of the principal sections i.e. by that I mean the tangents of the principal sections at a point. Tangents to these curves to the principal sections are called principal directions. And they are mutually orthogonal, जो कि हम आगे दिखाएंगे. They are mutually orthogonal. Okay, so I think I will stop there right now. हम फिर next time करेंगे, कल तो नहीं करेंगे, परसों